In this example, we look at the normal approximation for the proportion of M&Ms. In the last example, we looked at the proportion of blue M&Ms, and we looked at data from a class sample. The class sample had very small sample sizes, just 10 M&Ms counted at random. So we left off thinking about how we could get more accurate or convincing results. So we did answer increase the sample size of the M&Ms to the previous question. So here are some computer simulated dot plots of the proportion of blue M&Ms corresponding with different sample sizes. In the first graph, n equals 10 is the sample size of M&Ms, and each student sampled once. So this is similar to the graph that we looked at from a different class, but we see the dot plot here has a center around 0.2 or 2/10. The second graph is n equals 20 M&Ms sample size, and in this graph each student sampled twice, so there are double the data points and twice as many M&Ms in their sample. So think about dividing by 10, we get decimals like 0.1, 0.2, 0.3. If we were dividing our count of blue M&Ms out of 20, we get decimals like 0.10 or 0.15 or 0.20 because we're dividing by 20 now. So our decimals will go in increments of 0.05 when the sample size is 20. And so we see here we've got values at 0, 0.05, which would be 5% of the M&Ms were blue, 0.10, 10% of the M&Ms were blue, all the way through, it looks like 0.35 here. In the third graph, n equals 100 M&Ms sample size, and each student sampled 3 times. So we have a bigger sample size here and 3 times as many dots because students were sampling 3 times in this simulation. So if you think about dividing your count of blue M&Ms by 100, you could see, well, any decimal to 2 decimal places would be possible. So we see our values here go from a little above 0 all the way up to about 0.27 or 0.28, and our center looks to be a little bit below 0.18. Statisticians use computer simulation to save the time of sampling repeatedly, and we are able to simulate because we know that long-run behavior will be predictable. So we want to describe the similarities and differences in the graphs above, and we want to make sure we know the center, shape, and spread for each graph. So we notice as the sample size and the number of samples increases, the shape looks closer to a normal distribution shape. So when the sample size was 10, the center was around 0.2, and the range was from 0 to 0.4. So that would be from 0 out of 10 M&Ms being blue to 4 out of 10 M&Ms being blue. When the sample size was n equals 20, the center was around 0.2 or 0.20 again. And our range now is from 0 to 0.35, so our range is a little bit narrower. 0 is still 0 out of 20 M&Ms blue. 0.35 would be 7 out of 20 M&Ms being blue. And then when n equals 100, our center got a little bit lower. I said it's around 0.16, estimating from the graph. And then our range here is from about 0.02, so 2 out of 100 being blue M&Ms, all the way up to 0.28, which would be 28 out of 100 M&Ms being blue. So in the graphs above, what we see is that if we have a large enough sample size and repeat the number of samples from the population many times, the histogram of the sample proportions, or if we're doing quantitative data, we call our samples sample means because we'd be looking at numbers, looks almost like a normal distribution curve. So in order to use a normal distribution approximation, our rule of thumb is that the sample size times the population proportion must be at least 10, and the sample size times 1 minus the population proportion must also be at least 10. So as formulas, we write n times p is greater than or equal to 10, where n is the sample size and then p is what we expect the population proportion to be. And the other formula we have to check is that n times 1 minus p is greater than or equal to 10. So our sample size times everything else that's not that proportion we're studying. Some statisticians prefer to say 15, or at least 15 instead of at least 10, but we will use 10 as our rule of thumb. And then this rule of thumb is often called the rule of sample proportions. All right, so according to the M&M factory employees' claim, they said the population proportion is p equals 1 out of 6 or 0.1667. So we're going to assume this is true. And then we are going to carry out these calculations to try to figure out the appropriate sample size. So in the first column of the table here, we say, what if n equals 20? So we'll double our sample size. And we're still assuming p equals 1 out of 6 of the M&Ms are blue. So we multiply here, n times p, and that would be 20 times 1 out of 6. And you could do this as 20 times 1 is 20 over 6, or you could do it by converting 1 out of 6 to decimal. And so we get that we would expect 3.333 blue M&Ms in this sample. So this is an expected value, so of course you would never actually get a decimal. You would expect to get somewhere between 3 and 4. And then to calculate n times 1 minus p, that would be 20 times 5 out of 6, where 5 out of 6 are the M&Ms that are not blue. And so when we multiply, that would be 100 out of 6, or 16.6667. So are these values at least 10? And n times p was only 3.333, so that's not large enough sample. So when we say, is this a large enough sample to use a normal approximation, we can put a big no here and say our n times p, our expected value, is less than 10. The n times 1 minus p was big enough, but both values needed to be at least 10. So let's go even bigger. Let's go up to n equals 40 sample size, still using p equals 1 out of 6. So this would be a random sample where we would count out 40 M&Ms at random. So 40 times 1 out of 6, well, that's 40 out of 6. When we divide, we get 6.6, and the 6's keep going. So you could round, or I put a bar above my 6 in the decimal place to show it keeps on repeating. And then n times 1 minus p, well, that's 40 times 5 out of 6. 1 minus p is the M&Ms that we don't expect to be blue, so that's 5 out of 6. That works out to be 200 over 6, or 33.3, with a bar on top to show the repeating decimal. So that count would be more than 10, but the n times p, the expected value count, is not quite 10, so we could not use a sample size of 40. That's still not large enough, because when we multiply 40 times 1 out of 6, n times p, we get a value less than 10. All right, so let's go up to an even bigger sample size. Let's imagine n equals 60 M&Ms selected at random, and our population proportion is still 1 out of 6. So 60 times 1 out of 6 is 60 over 6, or 10. So we're in business here. We've got at least 10 for our expected value. 60 times 5 out of 6 is 300 over 6. So that would be 50 M&Ms that we would expect to be a different color, not blue. So a sample size of n equals 60 is large enough to use a normal approximation. So we can say yes here. Now, I also went ahead and said yes to sample sizes n equals 80 M&Ms and n equals 100 M&Ms without doing my calculations, because I know if 60 is large enough, the expected values for 80 and 100 sample size would also be more than 10 in each group. So once you get to at least 10, you can assume any sample size larger than that would also be sufficient. All right, so based on our sample size calculations, we say n equals 60 is the smallest sample size of M&Ms we could use to get at least 10 blues and not blues. So now we want to start constructing some confidence intervals with an appropriate sample size. So here are point estimates for the proportion of blue M&Ms using sample size n equals 60, calculated from 10 students in groups, 10 different student groups in a statistics class. So you can see here, most of the points are between 0 and, or all of the points are between 0 and 0.4. And most of the points are hovered between maybe like 0.1 and 0.25 or so. So we want to figure out, well, what's going to be a typical error for these point estimates? So the standard deviation associated with an estimate is known as the standard error. The standard error describes a typical error or uncertainty associated with a point estimate. So very similar to the standard deviation, and we'll use it in many of the same ways. So we want to calculate the standard error for the population proportion p equals 1 out of 6 and the sample size n equals 60 M&Ms using this formula here. We've got a square root of p times 1 minus p all divided by n. So this is our formula to find the standard error for proportions. For any problem with categorical data where we're working with proportions, we will be using this formula. All right, so let's do our calculation, and then we're going to round our results to the hundredth decimal place for the ease of graphing. All right, we're using the population proportion p equals 1 out of 6. This is the proportion the M&M employee gave us, and we're going to assume it's true. And then we're using a sample size of n equals 60 M&Ms. So our standard error, I call it SE for short, is going to equal the square root of 1 out of 6 times 1 minus 1 out of 6, all divided by 60. So the 1 out of 6 represents the proportion of M&Ms we expect to be blue. The 5 out of 6 represents the proportion of M&Ms we expect to be not blue, to be some other color. And then we're going to divide that all by 60. So you can work through this on a calculator. Don't forget to square root at the end. And so when I did my calculation, I got 0.0481. Rounded to the 100th decimal place, that is 0.05. So now we are going to use one standard error as our margin of error. So we're going to plot the margin of error extending on both sides of each point estimate so that we are now plotting an interval of possible values, not just a single point estimate. So if you look at the next page, I took that original diagram from the class of 10 student groups, and then I extended the margin of error, my best estimate of 0.05 on each side. So those little purple lines outside the point estimates are my best estimate of how far 0.05 is. Typically, we're going to let a computer draw these graphs for us, but in this example, we look at how it would go by hand. So now we draw a vertical line through the M&M factory employees claim population proportion, p equals 1 out of 6, or 0.1667. And then we want to figure out how many of the intervals contain the M&M factory employees claim population proportion, p equals 1 out of 6. So up here, back in this picture, my green line through here, through 1 out of 6, is about where I think 0.1667 or 0.16, 0.67% would be, so a little before 0.2. And so I went through 4 different intervals here with my line through 1 out of 6. So I said 4 out of 10 intervals contain this population proportion, p equals 1 out of 6, or 0.1667. So 4 out of 10 is 0.4, or 40% of the intervals. So these intervals that we have drawn are known as confidence intervals, since there's a plausible range of values to predict the true population proportion of blue M&Ms. The point estimate is the most plausible value we have, since it was collected from sample data, so we build the confidence interval around the point estimate. For these intervals, the margin of error corresponded with one standard error. Since we have sufficient data that the sample distribution is approximately normal, we captured the middle 68% of the data. So we can say that we are roughly 68% confident that we have captured the true population proportion of blue M&Ms in our interval. So if we want to increase our confidence in our calculations so that there's not much room for doubt, how far should we extend the margin of error, and how confident will you be in your calculations? So to capture enough data to be confident we have the true population proportion, we can extend 2 standard errors for a wider margin of error. So 2 standard errors corresponds with capturing 95% of the data. We know that from the normal distribution relationships. So our margin of error here is going to be 2 times the standard error, or 2 times 0.05, which is 0.10. So now on the next graph, I have constructed intervals going out 0.10 with my best estimate with my drawing skills. So I've got my dots in the center of the interval. Those are my point estimates from each sample data from these 10 groups. And then I tried to draw out the margin of error 0.10 equal to 2 standard errors. Then I drew a vertical line through the M&M factory employees claimed population proportion of 1 out of 6. So that's the green line here. So a little before 0.2. And so we can count up the intervals that contain the M&M factory employees claimed proportion 1 out of 6. So it looks like this crosses through 8 out of 10 of the intervals, following my best drawing skills. So I said 8 out of 8 out of 10 intervals contain p equals 1 out of 6, or 0.1667 as a decimal. So 8 out of 10, that should say 0.8, not 0.6, is 80% of the intervals. So we have to decide, based on these calculations above, do we think that the M&M factory could be correct in the claim that they produce an equal number of each of the 6 colors of M&Ms? So at the 95% confidence level, it seems possible that the M&M's factory is correct, since more than half of our intervals contain the claimed population proportion p equals 1 out of 6. To be very convinced, we would like to see 80% to 90% of the intervals contain the claim. And here we do see 80% of the intervals containing the claim. So it does seem possible that the proportion of M&Ms for each color really are equal, because in our data we see that 1 out of 6 of the M&Ms could reasonably be blue, because 80% of our intervals contain that as a possibility. So in this example, we have constructed confidence intervals for categorical data. In this case, our categorical data is the proportion of M&Ms that are blue out of a random sample.